Welcome back. Till long day after. Today I will discuss abstract algebra just as a review. I will discuss the concept of center of a group, centralizer of an element of the group, and what is relation centralizer of an element of the group and center of a group, normalizer of a subset. I will discuss this topic as a review because in my previous video I have discussed obviously this topic elaborately. Today I will discuss this topic just as a review. Let's just recall what is the center of a group. If G be any arbitrary group, then the center of the group is denoted as, the notation is ZG, we all of us know this is actually set of those elements in the group which commute all other elements in the group. That means AB equal to BA, this is true for all B in G. Then the concept of centralizer of an element is, the centralizer of an element, the element considered as A in G is actually the largest set of elements that commute with A. That means the notation of the set is such type CGA equal to set of those elements G in capital G such that GA equal to AG. What is difference between center of a group and centralizer of an element? Centralizer of an element means here the element is fixed and set of those elements which commute this fixed element, this set is called centralizer. But center means set of those elements in the group which commute all other elements in the group. This is center. But here the element is fixed in centralizer. So the concept is centralizer of an element. And the concept of normalizer of a subgroup is, consider G be an arbitrary group and H be a subgroup of the group G, and given G belongs to capital G. Let G is G inverse means, or we all of us know this is equal to G is G inverse such that H belongs to H. Normalizer of a subgroup means set of those elements in the group G such that G is G inverse equal to capital H. That means that imply G is equal to HG. That means here set of those elements in the group which commutes with subgroup. Here set in the centralizer, set of those elements in the group which commute with one fixed element. But here set of those elements in the group which commute with subgroup. This is the concept of centralizer, normalizer, center. As for example, consider the set D3 which contain the element AB such that A cube equal to B square equal to AB square equal to identity, and the subgroup, consider the subgroup H1 and H2. H1 contain the set of element which 1 and B, and H2 contain the set of element which contain 1A square. Now check centralizer of H1, normalizer of H1, centralizer of H2 and normalizer of H2. For For this, since D3 contain the element AB such that A cube equal to B square equal to AB square equal to identity, that means this set contain 1A square, B, AB, A square B. Okay. Now, centralizer of H1 means obviously set of those elements in D3 which commute the each element of H1. If we consider 1, then obviously 1 commute with 1 and 1 commute with B. So centralizer of H1 contain 1. If we consider A, then A commute with 1. This is true, but in D3 AB not equal to BA, because in D3 AB equal to, obviously AB equal to AB inverse. Okay. Now, if we consider A square, then A square equal to A square, but A square B not equal to BA square, because since here AB equal to AB inverse. Now multiply this equation both side by A, then this would be A square B, which here AB inverse not, BA inverse, BA inverse, then this would be AB A inverse, and AB means obviously this is BA inverse, A inverse, that means this is actually B A to the power minus 2. So, A square B not equal to BA square in D3. So, centralizer of H1 does not contain A square, but it contain B, because B equal to B, B square equal to B square. So, this is contain B. Similarly, it does not contain AB and it does not contain A square B. Check it own self. So, centralizer of H1 only contain 1 and B. Now, we have to check normalizer of H1. For this, here the difference is set of those elements which commute whole H1. In centralizer, this is commute each element of set of those elements which commute each element of H1. For this, if we consider 1 H1 obviously equal to H1 1. So obviously normalizer of H1 contain 1. Now, if we consider A, then H1 equal to, this is contain AB. H1 equal to A, and this is BA. And in D3, AB not equal to BA. So here H1 not equal to H1A. So in normalizer of H1, A does not be the member. Similarly, if we consider A square, this is also not same element of H1. So obviously normalizer of H1 does not contain A square. But if we consider B, then B H1 equal to set containing the element B square, and H1 B equal to, this is also contain B square. So the set of element in B1H and H1B are same. So normalizer of H1 also contain B. Similarly, it does not contain AB and A square B. Check it own self. But when the subgroup H2 which contain the element 1a square, then centralizer of H2 equal to, obviously it contain 1, then centralizer of H2 also contain a, because a commute with 1, a commute with a commute with a square, so centralizer of H2 contain a. Similarly, centralizer of H2 contain a square, because a square commute with 1, a square commute with a square commute with a square, so centralizer of H2 also contain a square, but centralizer of H2 not contain B, because here B equal to B, BA equal to not, BA not equal to AB. So centralizer of H2 does not contain B, similarly does not contain AB, does not contain A square B. Now we have to check normalizer of H2, and this is very interesting. Normalizer of H2 actually whole D3, because if we multiply H2 with B, then BH2 would be set containing the element B, BA, BA square. Similarly, H2B would be B, AB, A square B. And in D3, obviously BA means A square B and BA square means AB. So notice here the set of element of BH2 and H2B are both equal. B A square B AB, here B AB A square B. Notice here the difference between centralizer and normalizer. Here the element same, but in centralizer always it is commute with fixed element, one fixed element. Okay, so here normalizer of H2 actually whole element is commute with this subgroup. Check it own self. This is very interesting. I hope my all viewers have understood by this question the normalizer of any subgroup and centralizer of an element. Okay, well, there exists some nice property of centralizer of A and normalizer of A. First property is, if the group is abelian, then since whole element commute each other, then centralizer of A would be whole group G, because then every element of the group obviously commute with A, then centralizer of the A obviously would be G. And if the group is cyclic, then obviously we all of us know cyclic means obviously the group is abelian, then centralizer of the group is whole group C. And if the element A be the member of ZG, that imply centralizer of A equal to G, and this is true for all A belongs to the group G. And if centralizer of A equal to whole group G, that imply class of A equal to singleton set A. I hope my all viewers have understood. These two property also very important. If A be the member of ZG, then centralizer of A equal to Z, and this is true for all A belongs to Z. Because A be the member of ZG means those element who is commute all other element of the group. And since this element be the member of ZG, that means obviously this is commute every element of the group G. So centralizer of this element would be whole group G. And second property, also very important, if conjugacy class of A equal to whole group G, that imply class of A equal to singleton set A. Conjugacy class of A equal to whole group G means obviously AX equal to XA, and this is true for all X belongs to Z. That imply A equal to AX A inverse. And since that imply A equal to AXX A inverse, that means class of A equal to singleton set A. I hope my all viewers have understood this concept easily. If conjugacy class of A equal to whole group G, then obviously class of A equal to would be singleton set A. Now I will say one example. For example, if we consider Q8 group, then obviously this is content plus minus 1, plus minus I, plus minus J, plus minus K. And we all of us know center of this group is plus 1 and minus 1. Then if we consider centralizer of I, then this set contain 1 minus 1 I minus I. Have you understood? Notice here 1 commute with I, minus 1 commute with I commute with I, and minus I also commute with minus I. Similarly, if we consider centralizer of minus I, then the set containing 1 minus 1 I minus I is contain centralizer of minus I, and centralizer of J is contain 1 minus 1 J minus J. Similarly, centralizer of minus J contain 1 minus 1 J minus J. Okay. And centralizer of K is contain 1 minus 1 K minus K, and centralizer of minus K contain 1 minus 1 K minus K. And other element is centralizer of 1. Since 1 be the member of center of Q8, so centralizer of 1 is obviously whole group G. Similarly, centralizer of minus 1 is whole group G, and G means is actually nothing but Q8. I hope my all viewers have understood this concept easily. Now I will see one nice relation between centralizer of an element and normalizer of a subset. Center always contain identity element. So this is always be the subgroup of G, those element who is contain center of the group G. This is also contain centralizer of the element A. Notice here in Q8, get Q8 equal to 1 minus 1, and centralizer of each element contain obviously this is also then other element. So actually center of any group is actually intersection of all centralizer of the A in the group G. And notice here intersection of all centralizer is obviously 1 and minus 1. So and notice this is be the member of center of Q8 group. So obviously ZG content in centralizer of A and the element of normalizer of any subgroup is also element of centralizer of A. So this is the big subgroup. I hope my all viewers have understood this picture easily. And this type of relation actually very important for her study. Okay? Well, today I will stop here. I hope my all viewers have understood the relation between centralizer of element and normalizer of a subgroup. Okay? See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.